Hello, my name is Hong Lee, and I'd like to introduce the experiment we're going to conduct. So today's contents are based on the vision-based pick-and-place task. So I'll introduce this material, including camera model, calibration, arc marker detection, and so on. So here in this video, our final objective is shown, which is pick-and-place. So as you can see in the video, there's a box that has an arc marker on it. You can detect this marker and estimate its pose using its pose data. The robot can pick up the box. So because the robot knows where it is located by the marker, and so we'll implement the pick and place algorithm using classical vision-based method. So I'll briefly introduce experiment 2. In the lecture video, we look at the pinhole camera model, which includes extrinsic and intrinsic parameters included in the distortion model, which are used for image projection. The camera's extrinsic parameters represent points with respect to the camera frame. In other words, they describe the rotation and translation from the world frame to the camera frame for the same point. The intrinsic and distortion parameters are used to obtain the pixel coordinates based on the similarity ratio and a projection. Our goal is to estimate the target pose using the camera. In other words, we want to know about the extrinsic parameters of the camera. However, since our given data consists only of images, we need to determine the intrinsic and distortion parameters in order to obtain the extrinsic parameters from the camera model. To achieve these, we need to obtain the intrinsic and distortion parameters through camera calibration. Then, by using the arc marker and the intrinsic and distortion parameters, we can obtain the extrinsic parameters using the solve PNP algorithm. I'll introduce the robot camera calibration process. First, you don't need to implement the calibration code. Just use the provided projection code. You only need to follow the instructions to obtain the intrinsic and distortion parameters. So please make sure the calibration corners are clearly detected. To do this, place the calibration board, which I'll give to you. This is the calibration board here. So I'll place the calibration board not too far away. And please note that to capture at least 20 images so that most of the camera's field of view is covered. The arc marker is a great tool for recognizing the unique ID and estimating the pose. By using the corners of the marker, we can determine its pose with the camera model, which includes the intrinsic and distortion parameters. The second step is to detect the arc marker. This step is straightforward with the OpenCV library. I recommend using OpenCV to detect the marker, read its ID, and estimate its pose. The third step is to build the grasping pipeline. First, use OpenCV to detect the marker and get the camera's extrinsic parameters. Then, change the marker pose to the grasping pose in the world frame. After that, use inverse kinematics to find the robot's joint positions. And finally, move the robot to that position and close the gripper. This is the grasping pipeline. You can follow the pseudocode or design your own algorithm. Please note that the arc marker's pose is different from the grasping pose, so a transformation is required. So please make sure to check this transformation process carefully. The final object is to perform pick and place by moving all the boxes to different positions using arc marker based grasping method. Three boxes will be placed at random positions near the robot. Your robot should place these boxes in other locations. Since the robotic arm's reach is short, please make sure to adjust the height by placing a big box underneath, as shown in this video here. This is a summary of the tasks, so you can refer to this slide. Okay, lastly, I'll talk about the evaluation criteria. In the second week, the maximum score you can get is 7 points. If you successfully perform the pick and place algorithm, you'll receive all 7 points. However, if it's unsuccessful, the maximum score you can get is 4 points. You'll get 1 point for conducting the camera calibration, 1 point for detecting the ARPA marker, and 2 points for completing the grasping pipeline. I'll introduce the deadline later. And if you submit within 1 week after the deadline, you will receive half of your total score. And if you submit later than 1 week after the deadline, you'll receive 0 points. The attendance rule is the same as before. And here, the deadline is 9 p.m. on the April 19th. And please submit your pick and place video and source code via email. So the video should include your student ID, date, and time, and it should also show the pick and place task before being performed.